I have one announcement. We're gonna have a final exam at the second week of the June. So I believe it must be officially noticed to the student. So did you guys already know about the schedule for the final exam? Okay, if there's no problem to the student, I'm gonna fix the final exam date. And I'm gonna notice again at the KakaoTalk and the LMS system. And it's gonna offline. Is it also okay? Okay, good. Okay, then let's start today's lecture. In the last class, I talking about the GMR, the giant magnetic resistance. The basic principle is understandable with these cartoons. Just a moment. Okay, so the basic idea of the GMR structure is when we have a two ferrite layer sandwiched by non-ferrite material like a copper, and the thickness of copper must be very thin. The thickness should be less than the spin diffusion length. And when the ferrite layer parallel and anti-parallel, they have a different resistance because of this scattering procedure for the spin up and spin down. As a result, when they parallel, we have a small resistance, while we have anti-parallel, the resistance is high. And because of this discovery of GMR, the Nobel Prize, the two scientists got the Nobel Prize, the Albert Ferrer and the Peter Gutenberg. Yeah. And I just simply explain the shape of the hard disk drive, the working principles. And in last class, some students asked me about the MR curve of the GMR. So I'm going to show two kinds of the MR curve. The first one type is here. Here, the two ferrite layer are anti-parallel at the field is 0, but they are parallel to the high field and the opposite negative direction with the negative field. In this case, in an anti-parallel case, the resistance is getting larger. And the resistance can be dropped very largely when they are parallel. And the value can be reached around 80% in this case. And the details of the MR value, this curve, depends on the thickness of the interlayer, in this case, a chrome. Then here is one question: why in a zero field they are keep the anti-parallel condition? So that's what I'm gonna explain. It's called interlayer exchange coupling. I'm gonna explain just later. after this view graph. Okay, this is one type. And the other type is we use the different parameter layer. One is called the fixed layer. And this layer can resist the external field very strongly. While this another parameter layer called the free layer, they can be easily switched. So to make such kind of structure, there are two ideas. One is called pseudo spin valve. And in that case, we made the hard parameter layer. So they have a large magnetic anisotropy, so they can resist to the external field. So while this free layer is designed by the soft parameter layer, so they can be easily switched by the external magnetic field. And the other way is called the spin valve, which is a very clever idea. They made they introduced extra anti-parameter layer. This anti-parameter layer is coupled with this parameter layer, and the magnetization direction of this parameter layer is fixed by this anti-parameter layer. So this bilayer system with the parameter layer and anti-parameter layer, we have a new phenomenon called exchange bias. That's another important physics, but unfortunately, we don't have enough time to explain this exchange bias system. But somehow it is very important in modern spintronics. Okay, so let's assume somehow we can fix the one parameter layer while the other one is free. So in that case, the loop is something like this. Let's imagine the MH curve. This part represents the switching of the free layer. They can be easily switched with the small field. While this loop, this part, represents the switching of the fixed layer. So in this case, we're gonna play with only small field. So important thing is here. Or in MR, we're gonna use this part. So in a small field, we can get a relatively large MR value. So this is the basic principle of the GMR usage. And I'm gonna explain about what is the inter-exchange coupling, which one is preferred the antiparallel coupling between two parameter layer. Yeah, I hope all students can remember RKKY interaction, which one I gave in a quantum mechanical, the fundamental basic of the magnetism of the quantum mechanics, maybe part 5 something. Yeah, this RKKY interaction means if we have a one spins, and if the interaction between two spins is mediated by the conducting electrons, the spin polarization is oscillating, and they can be plus or minus sign. So in some sense, in some distance, they prefer the parallel direction, but in the other distance, they prefer the antiparallel configuration. So in this RKKI model is for the atomic interaction. But just imagine if you have a two ferromagnetic layer, and there is each ferromagnetic atoms at the interface, and there's a non-magnetic layer here. And each atom, they have a coupling because of this RKKY interaction. Sure, there is some other coupling from here to here and here to here, but they're gonna cancel out each other. So as a result of this RKKY interaction, even though two ferromagnetic layers are separated by non-magnetic layer, eventually there is some coupling between this ferromagnetic layer and this ferromagnetic layer. And they preferred parallel direction or anti-parallel direction depends on the space layer thickness. So depends on the space layer thickness. In this range, they preferred the parallel configuration, and this range they preferred anti-parallel configuration and something like this. And especially in this range, there is very strong anti-parallel coupling, so they preferred such direction. If we increase field, in a zero field, they naturally preferred the parallel direction, anti-parallel direction. And then when they increase the external magnetic field, here, they are starting this anti-ferromagnetic coupling, but when they increase the field, eventually they're gonna be aligned to the parallel. Okay, that's the very important thing in a spintronic called the inter-ray exchange coupling. And this MH curve represents the well-known result. Let's zoom in here. In a small field, they like the they prefer the anti-parallel configuration, while they have a large field, they're gonna parallel. So in this MH curve is typical MH curve of the anti-ferromagnetic coupling of the inter-exchange coupling. Okay, so this algebraic model is so easy to understand this inter-exchange coupling, but the truth is there is some missing point of RKKY interaction. So many people call this inter-exchange coupling to the RKKY interaction, but they don't agree about that. So they're gonna explain with the quantum energy model. That's more physically correct. So I also preferred this quantum model to understand the inter-exchange coupling. Yeah, just to think about that. If we have a ferromagnetic layer and there is some space layer, and this is the energy barrier. In a spacer, we have some kind of free electrons, while in a ferromagnetic layer, there is some band structure, and also there is some band structure for the spin down and spin up. And as we already explained, two bands can be different. So let's think about that electron inside of this spacer layer. Because of these different barrier heights, the waveform of the electron in a spacer layer can be modified. And this confinement of the electron called the quantum well. And the quantum energy of this confined electron can be changed depends on this barrier heights. So we can calculate the energy difference of the quantum energy because of this tri-layer structure. So when we have a parallel configuration, the band structure for the spin up, spin down is something like this. But when we have an anti-ferromagnetic configuration, the quantum structure is quite different. Something like this for the spin up and spin down. The total energy of this parallel configuration and anti-parallel configuration is sum up of these two quantum energy. And let's compare two energies. Which one is lower? Yes, the lower energy is our ground state. So the system preferred the lowest energy state. So when we calculate the energy of the ferromagnetic configuration and the antiferromagnetic configuration, we can define the coupling strength or coupling energy. So there is some kind of representation. It somewhat looks complicated, but actually this presentation, this rather complicated mathematical presentation is quite similar to the RKQY. But still, there is something more here. In this equation, we can see the k vector, which one is actually in a space layer, not the Fermat layer. So this oscillation period, this d is the thickness of the Fermat layer, the anti-Fermat, sorry, this non-Fermat layer. So this equation represents the oscillation of the sign of the coupling because of this exponential term. And also, this d-square term represents the decrease of the coupling strength with the increasing the spacer layer thickness d. And also, this delta R1 and delta R2 means the difference of the reflection coefficient for the spin up, spin down at the first and the second interface. So in this equation, you can easily imagine if we alter the reflectance difference, or if we alter the thickness and the Fermi surface of the spacer layer, we can modify the coupling strength. That's the very important understanding. Okay, so somehow, if you make such kind of interchange coupling, you can obtain, for example, in a strong antiferromagnetic coupling, this is the very strong antiferromagnetic coupling configuration in this thickness for the chrome. So in this zero field, they are antiparallel. And with the large field, they are getting parallel, but in a middle field, they are still heading the different directions. But if you change the thickness of the chrome layer, just in this case, 9 angstrom means around 3 or 4 monolayer, the coupling, the strong antiferromagnetic coupling disappeared, and all spins are parallel with the small field. And again, in a 6 angstrom more, we have another antiferromagnetic coupling here, and with the can be saturated with a large field. But here, we have a 10 kilowestel, while we need only 3 kilowestel, means the coupling strength of the 26 angstrom is much smaller than 11 angstrom case. Just like this. Or we can obtain such kind of loops with the inter-exchange coupling. So this inter-exchange coupling is also very important concept in modern spectrometry devices. Okay, so I just finished the very basic physics of the GMR and the spin valve structure with the inter-exchange coupling. And I'm gonna explain about the another MR called the TMR, or means the tunneling MR. Before move to the TMR, if you have any question about the GMR or inter-exchange coupling, yeah, you may ask questions. No questions? Okay, then I'm gonna move on to the TMR. Let's remind the tunneling effect, which we already learned in quantum mechanics. The tunneling effect occurred when we have a very thin energy barrier. Yeah, quantum mechanically, even the barrier height is large and the thickness is large, there is finite possibility of the tunneling. But if we play with the thin and moderate height of the barrier, the tunneling effect can be large. So it's very important. And as we already explained, this tunnel effect is impossible in classical physics. And also, this tunnel effect is also very important in scanning tunneling microscopy and many modern devices. Okay, so we already learned the Fermat layer is consisted by two different bands called the spin up or spin down, or in other words, spin majority or spin minority band. So let's think about this simple density state for the Fermat layer. When they have a parallel, the band structure of the Fermat layer is something like this, and this is the majority, and this is the minority band. And when tunneling occurred, they conserve the spin direction, so this upspin can be tunneled only to the upspin. And in a downspin, they can tunnel to the downspin. But if we have a antiferromagnetic configuration, means the left and the right electrode has a different sign, the different magnetization direction, and the band structure of this case, we have a same one. But in a opposite direction band structure, we have a different spin up, spin down band. So when we have a tunneling in an antiferromagnetic case, the spin up band tunnel to the spin up band in a right hand side, but in this case, this spin up is the minority spin, while this spin down is a minority in a left hand side, but when they tunnel to the right hand, they're gonna majority band. So the important thing is here, in this tunneling, this depends on the density of state of the each electrode. Means in this tunneling, we have a tunneling current of the spin up in the left side, spin up down side, the right hand side, and spin down in this case. But here we have a spin up in the left hand side, but spin down the right hand side. In this form. So it is quite similar to the GMR case. So as a result, the conductivity of the antiparallel and the parallel configuration can be different. And this MR ratio can be defined by the conductivity of the antiparallel and the parallel case. And with the simple calculation, we can obtain this TMR can be determined by this relation. Here, the P left, P right implies the spin polarization. Means the difference of the conduction electron for the spin and spin down. So in a perfect TMR can be occurred, the 100% of polarization means this is 1 and this is 1. So we have a 0 in a denominator, means we have an infinite TMR. But the truth is the p-value of the typical ferromagnetic layer is around 0.5 to 0.7 something like that. But still, we have a large MR compared to the GMR. So this is called the TMR structure. Okay, so is it okay? Can you understand what I'm explaining about this band structure? No problem? So with this discovery of the TMR, people immediately imagine the new kind of the recording device called the magneton resistance random access memory. So here is basic principle. If we have a antiparallel configuration of the spins, and if we send in the current, this current is not spin polarized. So spin up, spin down current are same. But when they are passing through this bottom electrode, the spin is polarized. Only the blue spin is dominant. But if you passing through this red layer, which one is the opposite direction to the bottom direction, then the current is smaller. But if we have a parallel configuration, this blue spin can be easily passed through this tunneling junctions. So the resistance of this parallel configuration is much smaller than this anti-parallel configuration. So we can distinguish the spin direction of this ferrite layer. This is called the free layer or recording layer. There are several names, but they are means also the same. So with this idea, I want to recall this figure again. We can make the good MR sensors. For example, this is the hard disk, typical example of the hard disk drive head designs. And here we have a free layer and non-magnetic space layer and second ferrite layer. And also there are something more, and there's some anti-ferrite layer. This is the typical configuration of the MR sensors, and there's something more, but it's too much to explain here. But anyway, the most important part of this sensor is a full layer and the space layer with another ferrite layer. This space layer can be metallic system. In this case, we call it GMR. But if we play with the insulator, we can form the TMR head. And also, there are something more between these other layers, and they are all important physics in modern spintronics, but I'm going to skip it here. So this TMR can be good hard disk drive head or can be a good magnetic sensors. But most important application of TMR is the memory. I'm going to remind you about the DRAM, which one is the volatile memory, and the DRAM means the dynamic random access. If you don't remember about the DRAM, please take a look. I recorded a lecture just beginning of this semester. And GM structure, DRAM, they consist by one transistor and one capacitor. And this kind of basic structure for memory is applicable many kind of memories. But in this DRAM, the most important weak point is volatile. The information is will be disappeared with tens of microseconds. So there is some comparison. If you store the water in a basket, but this basket has many holes, so DRAM has some leakage water or leakage current. So the stored water will be disappeared eventually. That's the very important weak point of the DRAM. And in other kind of RAM called SRAM is there is some no holes, so you can store the information, but it's very big. So how you can make the small basket means we can store more information without such kind of leakage. So this MRAM is small and they don't have any leakage water. So this additional water means we need a refresh of the information. Or in other words, we have to use the extra energy to get the information. So with this idea, people try to make the M-name structure, which one is I already mentioned in a previous class. So please, I hope students can remember this asteroid curve with the field-driven M-name. So if we make such kind of MTA array with such kind of lines, we can store the information in one parameter layer, and we can read out this information by the TMR. So basically, this side is quite similar to the long times the multi-core memory. Yeah, this array structure is all the same for many kind of memories. Okay, so when in a MNAME, if we want read the signals, we can send in current to this direction. So we can measure the MR in these specific cells. While if you want to write down some specific cells, we can send in current to this direction and this direction. Only this red cell should be switched. But the truth is not that simple. There are some unwanted switchings, and finally, the industry gave up to develop this MNAME because of some many technical problems. There are many important problems called, there are many minor problems, but the two major problems called the scalability and the selectivity. And scalability means if we want switching the magnetic cells, we need the external magnetic field. And if magnetic cell dimension is getting smaller and smaller, means we can increase the density of the memory, and we can, in other words, it's better memory. Then the required count is getting larger. So that means if you want to make the small memory array, we need a very large field, means we're gonna use more energy. So it's the very bad idea. But if you introduce new technique called the spin transfer torque, then the required current is scaled down. So if we make the smaller cell, we need a smaller current. This is very promising. And another one is the selectivity. As we already explained in a previous case, if you want switching one cells, and only that cell should be switched. If other cell is switched, that will be a problem. That kind of a problem called the selectivity. So in the spin transfer torque, we can select specific cells which we want to switch. So this is a perfect selectivity. And another important problem is the TMR value is not good enough. Even though we have a somewhat large MR in a TMR structure, the order of 50 to 50% something. So it is very large signal compared to the AMR, which one is only 1%, and GMR is around 10%. This value is quite large, but still it is not good enough. So in addition to these two problems, we have another one. There is not enough signals. So I'm going to explain about this MR in this chapter, and we're going to switch. We're going to move on to the spin transfer torque, maybe next class. Okay, so let's back to the TMR again. TMR, I just explained briefly about the density of state contribution in this simple band model. And let's recall the tunneling theory. In a tunneling barrier, we have a tunneling current in this form. Here, This is the Fermi direct distribution for left and the right hand side, because we have a energy difference of the if you apply bias voltage V, we have a such energy difference. And there is some tunneling probability, which one is already we obtained by the WKBF approximation. And also, there are another important thing. This is the density state of the spin down. So with this formula, we can obtain the TMR value, and with a simple assumption, we can obtain the simple value, simple result. The TMR value is only proportional to the spin polarization. And the spin polarization means the difference of the spin up, spin down energy, density, the number of carrier, and the difference of the spin up, spin down. Okay, so that means if you select the ferromaterial layer, yeah, this information is only the ferromaterial layer. And this Julius model implies the TMR cannot be depends on the insulator layer. The TMR value is only depends on the ferromaterial layer, and in order to obtain large TMR, we should increase the polarization of each electrode or each ferromaterial layer. So TMR depends on only density state of the electrode, and there is no bias dependence, no barrier material dependence. And this Julius model is quite correct, but it's too simple. But it is sometimes good enough to understand the basic idea of the TMR. But people want something more. We need a higher TMR. So after discovered TMR, actually that one is discovered very, very long time ago. But in that time, very small value. But in middle of the 90s, there is some meaningful finding of the TMR, which one is observed in room temperature, and easily they can achieve the 50%. But after people investigate more deeply, they found even much larger TMR, and now it's around 1,000%. And the funny thing is, this can be achieved by MGO layer. We call the measure of the MGO. The funny story of this MGO TMR, we call sometimes this is the MGO TMR, or huge TMR, or a giant TMR, because they are much larger than the other TMR systems. Actually, many physical finding, solid state physics, the experimentally find something new phenomena, and then theorists try to understand what's going on in that new systems. But in this in this giant TMR, it's very unusual case. There are some theoretical predictions. Some theorists predict if we make such kind of structure, we're going to have a large TMR. And then experimentalists try to make this kind of samples, and finally, the prediction is correct. Yeah, so there is some funny story. The theorists who proposed this large TMR, they didn't file the patent. If they make a patent, they're going to make a lot of money. So many people ask the question, you didn't make a patent with that idea? And the answer is funny. The theorist said, oh, I never imagined they can be realized, because they assumed perfect crystal structure. And that is not easy to make such samples. But people, experimentalists, found if you make such sample, it's gonna be. So somehow they tried very hard, and eventually they made such high quality samples. So the theorists got a good chance they can make a lot of money. So that is one lesson. If you have a great idea, then please make a patent whether it is realistic or not. Okay. So after we made such kind of TMR structure, there are many applications because we can much larger and much bigger signal to NAND and hard disk drive head. And there are many successive findings related to that one. Then what's the magic of the MGO layer? Yeah. So let's compare to the TMR, earlier TMR, which was made by the typical insulator layer made by the aluminum oxide. And in aluminum oxide, that's they form the amorphous phase. So when we have an electron here, and they make a tunnel structure, tunneling the aluminum oxide layer, the tunneled electron has some dispersed characteristic. Okay. Then while we have a MgO layer, they're gonna form very nice crystal. So the electron can be tunneling with the ghost rate. Yeah, I'm gonna explain this more physically. This is maybe too much simple. So, okay, TMR with the aluminum oxide layer, they have an order of 50% of the MR. This is good enough, but not good enough for the practical application like MNAND. So as I already said, this guy predicts the giant TMR in the ion MgO ion perfect crystal systems. So this is more than Julius model. And here is the key idea is the band structure of the MgO and ion. And also this epitaxial crystal growth is very important. Okay, so this is the MgO case. This is aluminum case. Yeah, this is MgO. Yeah, something like this. Here, ferromatic ion or cobalt or alloyable ion cobalt, there is some kind of three bands in a Fermi level called the delta 1, delta 5, and delta 2, and delta 2 prime. In a MgO structure, this is the perfect crystal. So this momentum of electron can be conserved during the tunneling procedure. So this delta 1 band tunnel to the delta 1 band, delta 5 to the delta 5, delta 2 and 2 prime to the delta 2 and 2 prime. But in aluminum oxide, this is the insulator, amorphous. So they cannot conserve the momentum of the electron. So this delta 1 band can go to delta 1, delta 5, delta 2 prime, 2 and 2 prime. So any band. So this MgO case, we call this is the linear momentum conservation tunneling, while this aluminum oxide, we're gonna lose the linear momentum. That is the very important. Let's take a look at this band structure. Here, this is the ion band structure, and this black one, the bold one, is delta 1 band. The spin up, but this delta 1 band for spin down, there is something here. So in the sense of the delta 1 band, the upspin, they are close to the band, the Fermi level. So there's some conduction electrons. But for the delta 1, for the minority or spin down band, the band structure starting here. So there's no cross with the Fermi level, means there is no delta 1 down band, down electron in a Fermi level. So if you take a look, if you think about the delta 1 band, this ion is perfect half metal. That means only one spin polarized electron can be exist in a Fermi level. So in a delta 1 band, ion is there is only 100% spin polarized electrons for the delta 1. But in other band, actually this is the other band for the spin up, spin down. They are all in a Fermi level. Even though this down band have this cross here, while the spin up band there is something here. So there is a non 100% spin polarization. So in an aluminum oxide layer, all this band structure is stopped. But in an MgO case, delta 1 band tunnel to the only delta 1 band and delta 5 to the delta 5. So yeah, it's same for the cobalt. So in a delta 1 band can be tunnel the tunneling decay length is getting smaller. So there's a finite tunneling. While this delta 5, delta 2 has a more rapid decrease of the tunneling probability. So in other words, with the MgO layer, only delta 1 electron play the important role. So without disturb of the other band, only when you consider these two bands, the spin polarization is close to the 100%, and finally we can get a very, very large TMR values. So in first principle calculation, they can find the transmission coefficient with the MgO layer. In the majority band, there is a very strong transmission in a gamma point, means the center of the band structure. While in a minority conduction occurred very small value at the edge of the Brilliant zones. And in a parallel configuration, there is also very small transmission. So in a parallel configuration, the transmission is something here, while the transmission of the anti-parallel configuration is more than smaller, 10 times smaller than the parallel configuration. So we can get a large MR. So that's what we call the spin filtering effect. So in this figure, tell us in a K, scale of the K and the energy. Here's the balance band and the conduction band, and here is Fermi level in MgO. So when they calculate the band structure of the MgO, this is the K square, but we have a negative value here, delta 1. Means the K value is imaginary and there's some finite decay. But this value is quite small compared to delta 5, delta 2, which one is a large negative value, means large decay length. So in other words, if you think about this ferrometer layer, another ferrometer layer, as we said, in a parallel configuration, this delta 1 band can tunnel only this delta 1 band. And this minus band tunnel into this here. And this difference of energy can be easily modeled by this simple barrier model. Even though this MgO barrier we modeled by the simple barrier model, but we can imagine in a delta 1 we have a small barrier, while delta 5 is getting higher barrier and delta 2 is even higher barrier. So the contribution of the delta 1 will be more dominant compared to other band. So that's the simple explanation of the MgO TMR. Okay, so this is the TM structure of the MgO layer. And this is the MB growth TJ, but this is the sputtering growth one. but still we have a quite good crystallized structure of the MgO. Okay. So the key issue is how we can cross the epitaxial MgO in a ferromantle layer. Yeah. Actually, when they discovered this MgO barrier, it was starting at the beginning of this century. Many professors crazy about that, how we can cross this MgO layer. They pushed the student very hard. Please make the MgO layer. But many students struggle to find the recipe to cross this MgO layer. So, yeah, this is a real story. At that time, many students just quit their laboratory because they failed the growth of the MgO layer. It's very hard, very tough one. So anyway, there are many key points to cross the MgO layer, and now many labs can be successfully cross the MgO layer, but still, it is not very easy task. So anyway. If you can find any other kind of the buried material instead of the MgO with the such a spin filtering pad, you can make a patent and get a lot of money. Yeah, but I'm sure it is not easy because people try to many materials already. But please don't give up. If you have a good chance, yeah, you can find some good materials. Not only for this TMR, but you can do any kind of material system. That's why we are working on in material science division. Okay, so this is the end of the TMR things. Couple of minutes. Before going to next chapter, do you have any questions? Didn't please tell me with the mic. I can understand your question correctly. Which page? Okay, let me answer about the one chance question. His question is about why the covalent boron has a large TMR. Yeah, actually, the magic of MgO is came from the band structure of the ferromantle layer, and the covalent ion has quite similar band structure, despite they have a different crystal structure. But in an alloy of covalent ion, we already know about the strata Pauling curve, where the number of electron and the magnetic moment has some peak here. This is the alloy of the covalent ion. And that means the spin polarization of this alloy is getting larger. So the TMR is also obtained large value at this alloy composition. Then what is the role of boron? Role of boron is not very clear because when we make the TMR structure with cobalt ion boron alloy, and then we can make annealing. And this boron is diffused out. So after annealing, we believe the cobalt ion forms the kind of a well-defined crystal. But with boron, with boron, the role of boron is we can make the amorphous phase first. Because when we cross the polycrystalline, there is some grain boundary. Then this grain boundary played as a kind of a pinning site during the multiplication switching. So with the grain boundary, it will gonna better switching behavior. So after with the boron at the first, we can make the amorphous phase, but after that we annealed it, then boron is diffused out, then the grain boundary effect is minimized. So the role of boron is something like that. So it is questioned what's the contribution of boron in a TMR, because the boron is diffused out and they segregate at the interface. And the interface is very important because the tunneling depends on the interface band structure. So, but the role of boron at that interface is far beyond of our simple model. They require many very careful calculations, the band structure calculations. Okay. So let me make a short answer to the one chance question. The role of boron is not very clear, but the cobalt ion itself, actually cobalt ion alloy has a large TMR for in wide range of the composition. That's okay. So in an RQQY interaction, here zero thickness means two teramet layer just without any non-multi layer. So that means this is the atomic exchange coupling. Then they should be very large. So in this idea, if you have something like this value to be atomic coupling strength, and is much larger than the interaction coupling. No. This thickness means the thickness of the non-multi layer. So if D is going to zero means two ferromulti layer is just touch each other. So this thickness means we can make each samples with different layer thickness. Any more questions? If you think about only delta one band, then 100% is correct. But in reality, there's no, it's not easy to obtain the perfect crystal. So if you have some misaligned crystal, there is some kind of mixture of the band. So, okay, let me make clear. If we think about delta 1 band, only 100% polarization is correct. But there is some still mixing of other band structure. And this is only for the one direction of the Fermi level, full band structure. Okay. So this is the example. Yeah, actually this calculation, this peak, okay, let's focus on only one layer thickness. This is the different layer thickness, so let's ignore this part. As you see, a majority band mainly came from this band center. So we can say here. While this minority band, there's some kind of conduction things in a large KX and large KY bell. In this two-dimensional one, if you take a look, you can have such kind of finite tunneling. So this corresponding to something here. Okay. So if you talk about the full band structure, we still have not 100% spin polarization. If we have a 100 spin polarization, then it should be 0. And let's think about that thicker fermat layer, thicker MJ layer here. Sorry. This is 4, 8, 12. Okay, if we have a thicker one, this transmission coefficient is for the majority band we have a 6 something, and yeah, this minority band we have a here. So it's 10 to 4 times difference. So in this thickness, the spin polarization is getting larger. So we have a large TMR. Any other questions? Okay, good questions. MGO, I'm sorry, RQQY interaction, we need conduction electrons. The base of the RQQY interaction called, there is some conduction electrons, and also in a spinel quantum model, we need the conduction electrons. So the insulator layer have a yeah, actually, insulator layer, we have a such effect, but it is much smaller than the the conduction materials. But still, MG layer, we have a finite interchange coupling experimentally observed, even though the value is much smaller. So you can imagine if we have some insulator layer between the space of place, then such quantum model is we have a not propagating wave, but we have a decayed wave here. But still, we have a different energy for the parallel and anti-parallel configuration. That means we have a chance to get a finite interchange coupling. But the magnitude should be very small. And this interchange coupling is strongly related with the spin transporter called the field-like torque, which we're going to learn. So this can be observed in an insulator layer. Yeah, I think this MR or this TMR things, it's not quite simple. So students need more understanding, and you need more time to understand, and you have to take a look more carefully. Okay, so let me close today's lecture here if you don't have more questions. Okay, so then see you Wednesday. I'm gonna upload the lecture note and additional homework. Oh, Uh, actually, the offline class things, last week, the school announced that the experimental class and some necessary class can be opened for the offline, but I, yeah, the situation is changed during this weekend, so I'm waiting the announcement of the official announcement from the university. So, students, do you want an offline class? Okay, so let me seriously think about that. Yeah. Okay, so let's talking about the offline class by the KakaoTalk. Okay. Okay, then see you Wednesday. But Wednesday we're gonna have an online one. But next week I will gonna decide if will be offline or online, and I will let you know. Okay.